Wow, I think all the important people are here, so it's a good time to start. Thanks for coming, everybody. Good afternoon. This presentation is almost a bit of a personal story. I did many enterprise service bus projects in the last 10 plus years, and then I looked into containers, and I remember like 2014, just across the road, I did the first presentation and said, look, WebLogic is running in a Docker container now. And there was about the same amount of people in the room, didn't count you now, but maybe 100, and I said, so whoever tried Docker just like a little bit, or who has a rough idea what Docker and containers are doing? And guess what? Out of 100 people, one guy raised his hand. I was like, oh, okay, good. I know those negative questions don't work, so if I say who has never heard about Docker and containers, people don't want to raise their hand. But I'm pretty sure now it's 90% plus or 95% plus. Yes, so my name is Frank Munz. I work for Amazon Web Services as a technical evangelist. Basically, I'm a software architect, DevOps engineer that is speaking at conferences. We try to inform and inspire people. When I submitted this presentation, I was more on the Oracle side. And I published a book about AWS like 2011, so a long while ago. And I focus on containers, serverless, do a bit of machine learning, and big and fast data. So the talk is about service bus versus service mesh. And I brought you, a copy of a diagram from a pretty good book, 6-8 years old, that is showing a really rough overview of what we understand about SOA. And what you see is that we have the bottom layer with the service implementations. That could be any kind of application, any language used, or any system that you want to talk to. And you typically have the clients on the other side of the service bus. And the service bus, what it's doing is service virtualization now. So it virtualizes the services, which sounds a bit academic, but at the end it means you're talking to the service bus the same way as you would talk to your services, and all the invocations go through the service bus, and this is the core principle. So it's a huge layer in the middle, and all the invocations to your service implementations go through this layer. And because it's such a huge layer, we have a lot of benefits from this. It's actually something that is meant to be online, running all the time. So you don't want to shut it down. And one key difference to those classical enterprise application brokers that we have seen before the service bus area is that this is configuration driven. And if you've been to any Kafka presentation in the last three years, you've probably seen a slide where they tell you, Kafka reduces the complexity, because if you connect all your services directly point to point, you have a squared complexity. And if you put a bus in the middle, this is reduced to a linear complexity, which makes a lot of sense. So if you need to change something, you just change the input or the output from the enterprise service bus. So this reduction in complexity makes a lot of sense. And in Kafka presentations, you see this, but it's a core architectural principle that existed even before. I don't blame them for using it, but Service Bus does exactly the same thing. And then we have this classical V2 pattern. It means validate, enrich, transform, and operate. That means we have an incoming message to Service Bus that is validated, because later you want to work with the message, and if you don't validate it, your XPath or XQuery expressions could just evaluate to anything, and you don't know what's happening. This is typically why we have this validate step. The message might be enriched, it might be transformed, and then you send it somewhere. So one thing that you can easily do with such a service bus, and this is what people were doing, is versioning. So in the service bus, you can decide based on some header or content value if you want to talk to a service implementation version 1 or 2. And very often it was used for this. In general, I would say it's doing cross-cutting concerns, like loose coupling, service bus is there to decouple the client from the service implementation. We get some kind of location transparency, because if you move the service implementation, you can adopt for this in the service bus. It can do throttling. That is very popular use case for service bus. Sometimes people are worried about performance. That is very often not the issues. But I've seen many projects where people tell you, well, I want the opposite. I want to make sure that you don't send me more than 1,000 requests per minute or whatever. Because all the invocations go through service bus, it's a perfect layer for monitoring, isn't it? If all the invocations go through there, why don't you count the invocations? Why don't you look how long those invocations take and so on? Same applies for security. You can apply security on the service bus layer. It's good for audit trails and so on. Now, what we see in the last 4 and 5 years is that those monolithic endpoints, let me go back once, those monolithic endpoints that you see on this bottom layer, those service implementations, we try to split them up and convert them into microservices. And the key question, and that's the topic of this talk, is if we convert our monoliths into microservices, is there still place for a service bus, or isn't there? Or isn't there something else that we could do more effectively? Now, splitting a monolith into microservices is not an easy task, and a lot of people talk about this, and I guess you heard many presentations about software engineering and how do you break a monolith into microservices. So there's a lot of aspects that come from a software engineering perspective, but there's also a lot of aspects that come more from a technical perspective, which is related to the protocols that we use, to the CPUs that we use, to many other factors. Now, I wanted to hide this picture. You've seen it now. The question I wanted to ask you is, who was the key driver, who's the key person that you associate with microservices? Who was the first who ever did it? And it was, it's Netflix. It's actually a company that is running 100% in the cloud. They have no on-premise data center, no on-premises database, nothing. It's 100% in the cloud. And the key driver was Adrian Cockcroft. He's actually working for AWS now, and he made a really good video that I want to show you quickly, talking about the technical aspects of splitting a monolith into microservices. Let's see if
this talks on the evolution of business logic as we went from monoliths through microservices, and now we're looking at functions. Back about 10 years ago, we had monoliths, and when we tried to split them up, we found that it was a lot of hard work. The networks were too slow, the CPUs were too slow, and the messaging protocols we used were based on XML and SOAP, and they were heavyweight. So when we tried to split things up, we ended up with fairly large services which had a lot of functionality in them, and we had a relatively small number of monolithic services that we built out. Moving forward a bit, what we found was that CPUs got a lot faster, networks got a lot faster, and we moved to much more efficient protocols. So it's maybe 100 or 1,000 times more efficient now to make calls between services. That let us take our monolithic services and break them up into microservices. Those services form a fairly complex looking network with a lot of messages flowing backwards and forwards between them. You can see here a service network, a service mesh, where we go from the edge, we flow through many layers of services to reach, on the right-hand side, storage services and caches. Now we take that environment, we think about the way that these services are becoming more standardized. So rather than building all these services ourselves, we're starting to use off-the-shelf services that are scaled, they're highly available, and they come from AWS. So we have SQS, DynamoDB, Kinesis.
Okay, let's stop here. The interesting thing I want to focus on is right here. If you see this, the question is there still space for an enterprise service bus? For such a scenario, would you use an enterprise service bus? If you have all those fine-grained microservices, how does it work together with a big monolithic service bus? The answer is, first of all, there is nothing against having one big monolithic service bus with microservices. Just because it's monolithic doesn't mean it's bad. No. The question is still, does it make sense to have a service bus implementation here. And let me go back to my slides. So one reason, well, the first question is, do people really have such microservices architectures, or is it something we just talk about in conferences? Who's implementing microservices from you? Wow, okay, that's even more than I expected. That's certainly 90% plus. So you all do it. I don't need to explain why we do it. If you look at what we do at Amazon, this is exactly our microservices. It's a visualization of our microservices that we run at Amazon. You know, we have those classical two-pizza teams where one small team is building a service, and they're independent, they're decentralized, and they work basically on their own service. In every service that you see here, it's hard to see, there's a small label on it. Now, again, if I ask you the same question for this visualization, do you think there is space for an ESB, for a company-wide enterprise service bus? And the answer is almost obviously no. And if you have been working with service buses, you also know why it's not possible to use a service bus here, because you need to configure them. You need to tell the service bus which service should talk to which other service, and you need to configure those connections. And that just wouldn't make any sense, because it's not possible with these amount of services. Right, so if you try to modernize this, and if you look at the technical architecture, talking about, you know, the typical TOGAF or whatever you do as a methodology in your company, if we look at the technical architectures, all the building blocks that we could use to modernize your applications were already mentioned in the video. First is containers. I think it's always containers. Now, many things these days we do with containers. We understand the benefits. They easily get us from development to production, because it's a great packaging unit that we can use to build those 12-factor applications. One of those 12 factors says that we should externalize the configuration. So we have a container image that is the same in development. We transport it to production. Well, don't really transport it. We put it into a registry and then pull it from the registry again. But it's the same image, and all the configuration that we need in addition is externalized. So it's a fantastic way to do this, and it's also a fantastic way to run in the cloud or to run on premises. So I think last year, 2 years ago, I was doing a demonstration here with my laptop, running 100-something Docker containers on a small laptop, and explained it works on a laptop, but it also works on a hyperscale at Amazon. This is why containers are so popular, and there's a good reason why they're so popular. The other thing that we talk a lot about that is not the topic of this presentation is serverless. It's a much higher level of abstraction where you just upload your code, you run your code, it's scaling automatically, and you don't care at all about the underlying infrastructure. Is it better or not? It depends. So I'm not the one telling you use this or use the other. I'm the one telling you carefully decide which one is better. If you want a higher level of abstraction, totally not care about the underlying infrastructure, it might be serverless, especially if you want to use this pay per invocation model, because then you only pay for what you really invoke. Otherwise, companies often want more control, and then they go for containers. And the third thing that Adrian also mentioned in his short video is cloud services. If there is a cloud service, use it, because the problem is solved. It's as easy as this. Now, a lot of people think about, should they stuff databases in a container and then run the container? I'm not against having stateful container, not at all. This is why we have things like Kubernetes and so on. But I think building your own database in a container that is distributed the way that we have databases now, like AWS Aurora is one, doing this yourself is incredibly amount of work, and you shouldn't do it. So running containers at scale is not easy, because they come and go, they're transient. It's a huge distributed system. Imagine you have 1,000 containers running, you need to start another one. Where do you place it? That's not an easy decision. And containers, they are not virtualization. It's not one operating system running on top of another. It's just isolation. We use C groups to limit the resources. We use namespaces, Linux namespaces, to isolate them amongst against other processes. So we need tooling, and the popular tool that we all know these days is Kubernetes. It's a rapidly moving open source project with a lot of enthusiasm around it. It's rapidly growing. It's a platform for running microservices at scale, and it offers a powerful abstraction layer that we need to schedule, to run, to orchestrate those containers. Now, we have a lot of container workloads running at AWS, and the main thing that people tell us is, please run Kubernetes for us. So last year I was here, and I'm not sure who heard the presentation, but I brought you a 4-node Raspberry Pi cluster, and I was trying to show you how to run containers on such a 4-node cluster with real hardware. And the key finding of this presentation is that I could show you with Docker and Docker Swarm, but it's almost impossible to do this from scratch without any Chef, Puppet, or Ansible script with Kubernetes. It's just too complex. So what customers want from us is that they say, please run Kubernetes for us. So there are managed container services in the cloud. The key problem very often is the master of the Kubernetes service, because it contains the etcd storage, where everything that you do with Kubernetes, if you say, well, create a service or create a deployment, is stored. And this etcd in the cloud service is fully managed. In our case, it's replicated across 3 availability zones. That means it's running across 3 separate data centers, and it's scaled. It gets provisioned IOPS. We run snapshots at regular intervals, so it will be backed up and it can be restored. And all that you see from this managed Kubernetes service is a fully qualified domain name. It's the endpoint of the API server. And then you can use your standard tools like kubectl and talk to it. And this is what people want. Now, in our case, if we talk about Amazon EKS, you can bring your own nodes. You can bring nodes which are spot instances where you bid on the price that you want to pay, a bit like in an eBay fashion. You can bring nodes with GPUs, where people say, why would you want GPUs for Kubernetes containers? There's actually lots of people running machine learning workflows, and they love to have those GPU nodes. And you can do whatever you want to do with your nodes. You can put them in an auto-scaling group, for example. Right. Looking at Kubernetes, there are some basic things that everyone should know. And the most basic resource is a pod. In a pod, we run one or many containers, and the pod has an IP address, but the pod comes and goes. It's this transient thing, so this is why we don't rely on the IP address. Then we have services, and those services, they provide a stable IP address for a pod. And then, again, this stable IP address for a service is not visible to the outside, and to have this, we need some ingress, and ingress basically is more or less a load balancer that is allowing connections from the outside to your service and your pods. This is why we create those ingress resources. Now, this is basic 101 for Kubernetes. And if you start playing with Kubernetes, that's the first challenge, to understand those resources and to be able to do this from the command line or from your YAML file. After a while, you see that Kubernetes is this extensible API that really beautifully works. And one of the resources is this admission controller. And the admission controller is a resource in Kubernetes that lets you run code after an API call. That means if something happens in Kubernetes, code can be run. And we need this just to understand the rest that I want to talk about. Now, coming back to the big picture, this is the ESB that I was talking about. And sometimes people call it's dump endpoints, intelligent pipes. Because all the intelligence is in the pipe, it's in the connection from the service left, connecting to the service on the right-hand side. And the pipe, well, the ESB is part of the pipe, is part of the intelligent pipe. But the logic that we need to do routing, to do versioning, to switch from version 1 to version 2, to do monitoring, to do security, it's all in the center. It's all in the service bus. Then we had a time, actually a very interesting time, and I remember this was like 4 years ago, 5 years ago. There were a lot of job ads where developers were sought, and in the job ad it said you have to understand OSS from Netflix. And OSS from Netflix is one of the first libraries. It's the Hystrix library, where they implemented a circuit breaker. And the key idea was you use this library basically at every service invocation of your code. And this is how to make it more robust, because everywhere you will have this circuit breaker used. But the thing is, it was a library, one language only, and you had to modify your code. Now, I just told you that this ESB, in my opinion, these days has this little question mark because it's this big monolith in the middle. But the big advantage, at least, it was language agnostic. Now you can use it for Scala or Python or Java or whatever. And this solution in the middle is only working for one language because it's one library, and you have to modify your code. Now the question is, couldn't we have the best of both solutions? And the answer is, this is what you get with a service mesh. And this is really nicely described in this InfoQ article. I put you the link at the bottom. So the logic is externalized. You don't have to change your code. It's working for all kinds of programming languages. Actually, the programming language doesn't matter. You just give it a container. The logic that is this cross-cut that is implementing these cross-cutting concerns is in a proxy. We call it proxy. And this proxy is not one big monolithic proxy that you need to configure like the service bus. It just happens to be automatically injected in your pod that is already running your container. And that's the beauty. So we take the benefits of both approaches, and that's the new one. It's called service mesh. And one very popular implementation, I'm not saying that this is the only one, but one very popular one is Istio. And Istio connects, secures, and observes services. That's the purpose of Istio. That's the best and easiest definition that you can find for Istio. And if you think about it, it's not really something new. It's nothing that you couldn't have done with the ESB 12 years ago. It's just a shift in where we place this technology. So we place the technology in a proxy, and then we kind of automatically create this proxy in every pod where we want to run a container. And we try and distinguish between a data plane, which is the set of all the proxies working together. And this proxy, it needs to be configured, and this is why we have a control plane, and the control plane is sending configuration to the proxies, and at the same time, the proxies are sending back telemetry data to the control plane. So they both work together, but they're not tightly married, they're not tightly coupled, they could be replaced. So for each side, there could be a different implementation. Now the proxy that is used is called Envoy. That's the name of the proxy. It was basically done by Lyft, not car sharing, the company that works like Uber. And they developed it, they open sourced it. It's incubating CNCF projects. I'll tell you in a minute what that means. It's open source, and it's working really well. To get the proxy into your pod, you have to inject it. Now, remember why I told you about this admission controller? This is something that can execute a step after doing something. So if you create a pod, if you set it up the right way, if your Kubernetes cluster allows you to do it, it could be forbidden, then you get this proxy injected automatically. It looks like this. Let me see if my pointer is working. No, it doesn't. Okay, it doesn't matter. So the key principle is, if you have a service A that wants to talk to a service B, it always needs to go through this proxy. So there's a proxy running in every pod. So every service that is talking to another service is going through the proxy. And remember, that's kind of the principle that I explained to you for the service bus. You always go through this big layer in the middle. Now we don't have a big layer in the middle. We have chopped it up into many small pieces. And actually, such a proxy, such an envoy proxy is 8 megabyte in size. So sometimes people are concerned and said, well, but then I have always this extra proxy running. It's 8 megabyte in size. That's 1/20th of a download of a JDK, for example. So it's super small. And you see also, that's the data plane, the sum of all those proxies. And you also see the control plane, which is the pilot, mixer, and this thing that is called Citadel. The pilot is used for configuration data, and the mixer is used for policy checks and for collecting telemetry. And I will show you this, hopefully, if the network is working, in a few minutes. Right. Now the question is, what could we do with this thing? And the answer is, if you give it a small YAML file that is very similar to what you know from configuring Kubernetes, from installing Kubernetes resources, you could do something really fancy that I like a lot. You could try and break your communication from service A to service B. We could do a little bit of, chaos engineering, where we try to break things in order to prove that they're really working well. So what we could do with this tiny bit of YAML file, we could add an extra delay in the communication from service A to service B. Now, the really cool thing is you never need to change your services. All we do is we kind of run or deploy this YAML file, and we only want to do this for 10% of the invocations. So basically, if your developers say, well, it's working well, we have the client on service A side and we have the implementation on service B side, and they show you a nice GUI and they say, look, boss, look, click, 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 it's working. You seem to be convinced now, but if you inject these errors for 10% of the invocations, you could see how your client is behaving if you have this delay. And that's super cool, I like it a lot. The same way we could have another YAML file that says, well, now don't route to service B version 1, but change it to service B version 2. That's also possible. But again, you don't have to change your services. So there are many things possible. The core of all this is this envoy proxy. Written in C++, it's a level 7 proxy. If you think about what level 7 means, it understands HTTP, it understands HTTP2, it understands gRPC, and actually understands, there is I think it's alpha still, but it even understands connections to DynamoDB, to database in AWS, or to MongoDB. Again, it's not specific for one language, it's more like the service bus that is language agnostic, and you need no code changes. So I think it has the best of those two approaches that I was showing you. So to summarize, again, it's doing cross-cutting concerns. Now, I didn't really want to compare which concern is covered by ESB and which concern is covered by service bus, by ESB and by the service mesh. But at the end, they both do cross-cutting concerns for services talking to each other and making this more reliable. There's retries, timeouts. You can have the circuit breaker. I showed you the YAML for the fault injection. Load balancing, client-side load balancing. They work with service discovery. You can enforce security between those proxies. That means your services don't need to implement security. The proxy does it for you. We can collect metrics. We can talk about deployments, and that's what I want to do next, and about traffic mirroring. You could just mirror your traffic and send it somewhere else. Okay, now, I'm not sure if anyone was here last year, but I'm still very proud about my Raspberry Pi cluster with these 4 nodes that I brought you. And I think at the end of my 45 minutes presentation, I was running a set of, I think, like 16 microservices on those 4 nodes of the Raspberry Pi cluster. And I said, look, it's so cool, I can do a rolling update of the service version. So one service was updated to 2, and then the next one was updated from version 1 to 2, and so on. And then after some services were updated, I was even rolling back the rolling update. And that makes me super happy. If I get that far in the presentation, I'm super happy. And I think this is what we did last year. Now, the thing is, shouldn't we separate the traffic flow from the replica deployment? And again, that sounds a little bit academic. This is why I was trying my best to bring you a really good animation. And it goes down to the question, if you update the service version of a deployed service, what do you do? Good question. How do you do it today? Now, one solution is you have this big switch, and you switch from version 1 to version 2. And I say, this is like you throw all your customers, let's assume you have like 10,000 connections on your service, and you throw all of them into cold water. Cold water because, well, you've tested your version 2, but are you really, really sure this is working? Do you want to throw 10,000 customers into a swimming pool of cold water? Do you know what happens if you're in cold water? You keep your breath, you hold your breath, and you hopefully don't freeze too much, because maybe you need to roll this back if it's not working, the version 2. You quickly need to roll back. Now, remember my Raspberry Pi story from last year? I said, you know, what we can do is we have those, in this case, 4 pods running or 4 services running, and I'm showing you the rolling update. So I'm updating 1 pod or 1 service at a time, and it's just replaced. And last year I told you this is a good solution. But the thing is, if it's 1 out of 4, it's still 25%. If you have 10,000 connections to your service 1 version, 2,500 will have the service 2 version. This is not a swimming pool of cold water, but this is still a bathtub full of cold water. And the question is, do you want this or don't you want this? Isn't the risk too big for 2,500 customers? So why not doing it this way? Why not just reshaping, changing the traffic and just sending like 3% or 7% or 1% of the traffic to the new version, which is, in this analogy, a little bit like you just wetten your feet. Now, can you do it with Kubernetes only? No, because we can do this rolling update, and we are very happy that we can do it. And this is basically what happens if you have a deployment and you update a deployment, it will do a rolling update for you. But getting from those 25% from this still big, massive mass of customers to 3%, you can do something like Istio. And I'm trying to show you this. Okay, so the Envoy proxy is part of CNCF. It's this Cloud Native Compute Foundation. They have different categories. One is the graduated projects, that is Kubernetes and Prometheus. And the other ones are called incubators, and Envoy is part of this incubator level. The question is, why is this any good? It's basically a connection of very popular, useful open source projects. Just did another presentation about big data, and maybe you've seen it. In big data, we have this huge slide where we probably show you like 300 or 400 different open source projects that you can use to do big data. And people always say, wow, how should I choose? And this Cloud Native Compute Foundation is a little bit like a safety blanket that gives you a pre-selection of projects that are incubating. Incubating also means that they have to have at least three implementations that are running in production, and then they can graduate and get on this level like Kubernetes. So Envoy is on this incubating level. That's just good to know. Now, if you want to install it, if you want to install Istio, what you can do is you can use a Helm chart. A Helm chart is like a package manager that you know from Linux. And you run Helm install. You give it a name, that's Istio. You can put it into a namespace, that is this Istio system, and this is all you need to do. So if you have this fully qualified domain name, the endpoint of the Kubernetes API, this is what you could run. That's one part. You see this slash at the end that tells you it's not the full story. And the full story goes on. If you want to have tracing, service graph, and Grafana running at the same time, you just add 3 lines, and then you have the full thing running that is Istio together with tracing, done with Jaeger and the service graph. And that's really cool. That's amazing. This is the first time when you start to realize often the power of Kubernetes. Now, this pre-built Helm chart lets you run the whole set of applications on any standard Kubernetes cluster. And this is where it becomes super, super powerful, when the whole abstraction of the containers is working and everything is working nicely together. Now, this installs it installs Istio. To make Istio run, you do some other neat trick that I like a lot. All you do is we put a label, which is called Istio injection. We set this label to enabled. We set it to true. And we label our default namespace. So in Kubernetes, you have a default namespace. And we just installed Istio in the non-default namespace with the name Istio system. But if you do anything like you just create a pod or you create a deployment, it will be in the default namespace. And this default namespace gets a new tag. And based on this tag, the auto-injection will happen automatically. So this is all you need to do. You install Istio. You label your default namespace with Istio injection enabled. And that's it. And I have 10 minutes left for a demo, which I will try. So let's see. Good. This is a good start. Let me restart this just to be sure. And also this. This is a port forwarding for what I have already installed, and I'm going to explain you this in a minute. This all looks good. And this is the command shell on my Mac, so this is local. And now I could say kubectl, which is the Kubernetes command line, and say get nodes. This is basically to check if the Wi-Fi is working. It's working well. You see I'm connected to a Kubernetes cluster that is running on EKS, on the Amazon Managed Kubernetes Service on the Amazon Cloud. And I have 3 nodes that are running at the moment. And I could also say kubectl or short K, because I have an alias for this, get pods, and you see the pods that I have running. And I brought you actually the standard demo that comes with Istio. Because if you try it yourself, you will play with this demo, and I think this is the easiest way to get started. And you see this demo, it's basically a book site that is giving us ratings and reviews, and there's some pods running right here. And if I say, give me the pods, but I want the namespace Istio system. Remember, this is where we told the Helm chart to Istio system. What was it? Yeah, I need 2 dashes, that's right. It's much easier if you sit on this side. Thank you. Okay, then you will see the Istio components like the mixer. You also see this sidecar injector. You see something that does string tracing and telemetry. Going back to the application, which looks like this. No. Well, this is how the cluster looks like on the AWS side. So basically, all we get is the API server endpoint. And the application, I think I lost it. Istio book info application. Just to show you, it looks like this. So it's a Python implementation of a product page that goes to Java implementation of the review that goes to Node.js for the ratings, and it can also display details with Ruby. So it's all mixed. It's different programming languages. It's hopefully running already, and let's see if this is replying. Yeah. So it's running, and this is how it looks like. So this is one way of getting the reviews. Now, remember I told you that one thing that we could do is we could change and there's 3 different versions of those reviews installed. So what I could do is I could say kubectl apply, and I want a file, and it's called version 2 is what is running now, and I want to change it to version 3. That would go like this. And if I say cat from this file, you will see it will take the reviews from version 3. So I have 1, 2, and 3 running at the same time. And if I switch back to this, it's black now. And if I change to the other version, it's turning red. So this would be a classical example of what you could do with Service Bus as well. Now, let's do something a little bit more exciting. Let's say kubectl apply, and I want to do something special for, let me see, some routing. Okay, I go back to my application, which is here. So now it's always going to the red stars now. So if I click reload, 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 I get to the red stars. Now, if you log in and you say, I want to log in as Thomas K, let's see what happens. Well, nothing happens. Now I log out again, sign out, I log in as Frank, and this is actually what is configured in the YAML file. You see it changes to black. So all the reloads now go to black. So now if I'm logged in as myself, as the tester, as the administrator, I get to one version of the service. If I log out and the public is getting to another version of the service, this is how you could easily test your service. And just to give you the file to see this, it goes like this. So there is actually, that's the other thing. Remember when I told you Service Bus is doing service virtualization? What they do in the service mesh, they call it virtual services. And this is the collection of all the rules and the attributes that you need to define a routing to a service. And here I say, if the headers match end user Frank, then route to version 2, otherwise route to version 3. Cool. The last thing I have prepared for you is traffic shifting. I think it goes like shift XY. And let's look at the file. Shift XY. Here we have the weights. And I could have done 3% and 97%, but it's hard to show. No, it's I had to click like 100 times, and then it's still statistics, what you will see. But now a lot more requests should go to version 2. Actually, 8 out of 10 and 2 out of 10 should go to version 3. And let's try this. So it's black, it's red, it's still red. Right. It usually needs a bit of time to kick in, but it's black, you see. Okay. I forgot which one should be 80%, but maybe we can tell. I think the black one should be 80%. We should see much more black stars than red stars. This is the way you get this wet in your feet only, where you send 3% of the traffic to one version to test it. And there's much, much more to do. You can just read up what possibilities you have in the YAML file. Just remember the fault injection that I was showing you. And let me switch back to my slides to come to a conclusion. One question is always, are people really doing this, or are you just talking about this like the things you talk about at conferences, but nobody's using it? Snap is doing this. Snap was talking about using Istio on a Kubernetes cluster that is running in the cloud. And I brought you the link. I'm going to upload the slides in a minute. There's a YouTube video from the CTO of Snap presenting about this. And I have some references. The summary is you should architect wisely. I'm not telling you to put everything in the container, but decide between container, serverless, and cloud services. Running Kubernetes is hard. A colleague of mine says if it's not working, and even if you're experienced, it makes a grown-up man cry. And I kind of agree. I had so many issues with my Raspberry Pi cluster. This is why I think you should strongly consider having a cloud service doing this for you. Service meshes, they complement Kubernetes. It's weird. First we tell you should do Docker, then we tell you need something on top that could be Kubernetes, and now I tell you need something on top that is the service mesh. But this is the truth as far as we know it. And the Envoy proxy, super interesting project. It implements those cross-cutting concerns that we know from the service bus. I'm not saying it's a drop-in one-to-one replacement, but this is kind of how the evolution of the architecture goes. And it nicely ties into those other tools that I didn't show you because of time restriction, that do visualization, Grafana, and other CNCF projects. If you want to connect to me, I'm Frank Munz on Twitter. I see the timeout sign. If you have a few minutes, and I think we need to stop the recording and so on, I'm going to show you the other things that you can do, visualization, flame graphs that you can get with Jaeger that we enabled with the Helm chart, and Grafana that we can use for monitoring the containers. We can also get a map of what is really happening with your microservices. That's a big step forward, I think, away from having this dot notation. Right. Thank you very much for being here. You've been a great audience. Thank you. I'm happy to take some questions offline. I think we just need to stop here. Thank you.